This is where we begin to take limits. So I take the limit as n goes to infinity of the nth term, which is this. This is the nth term of the sequence because I know how to do highest powers. I get n over n squared, which I know cancels, so I end up getting 0. In general, again, you take the limit as n goes to infinity, so you need to think about it. So if I plug in infinity, think about this term here goes to 0, so I get cosine of 0, which is 1. Here, if I take the limit as n goes to infinity, I'm looking at sine of infinity. So where does sine go as n goes to infinity? Well, that does not exist, because sine does not converge to any one number. Here I'm taking the limit as n goes to infinity of 3 to the 1 over n power. So 1 over n goes to 0, so 3 to the 0 is 1. Because you know the graph of arctangent of n, you know that this limit as n goes to infinity is pi over 2. So it converges to pi over 2. So when the limit converges to a number, the sequence converges to a number. I'm going to refer to this as the k-limit theorem. So when you're taking the limit of a number, k, to the nth power, if that number k is smaller than 1, then the limit is 0. And if the number k, as in this case, is larger than 1, then the limit is infinity. Sometimes we have to do a little bit of work to get to the k. So 4 to the n, and this is 5 to the 2n, so I can identify the k here is 4 over 25, so I get 0. So there are times when we want to employ ln rules, so this is one of those cases. So I do it, and I still get an infinity over infinity, so I want to use L'Hopital. So L'Hopital, changing to x's, you must change to x's in order to use L'Hopital, and then do the algebra to fix it. So I get 3 over 2x squared, so that goes to 0. So I guess I should say converging when it does go to 0. So here, if I take the limit as n goes to infinity, initially, I get infinity times 0. You know that's a case where you want to employ L'Hopital's rule, but you want to move one of the terms to the denominator. So I'm going to move this n to the denominator as 1 over n, but I'm changing to x's because I know I'm using L'Hopital's. So I get the derivative of the top over the derivative of the bottom. These two terms cancel, so I get cosine of 1 over x. As x goes to infinity, I get cosine of 0, so that's 1, so it converges. This one again, I'm going to need to employ L'Hopital's rule, and I will just put the e to the negative n in the denominator right away. So now changing it to x's and taking the derivative of the top and the bottom at the same time, I end up getting 0, so it converges. So here if I take the limit, I get the limit as n goes to infinity of sine of n over 3 to the n. This gives me a dne over an infinity. Not much we can do with that. If you think about it, you know that sine is bounded between 1 and negative 1. So if I divide everywhere by 3 to the n, in the middle I have the sequence that I want to show what it does. So if I can show the two other sequences go to the same number, and they do, therefore I know that the sequence in the middle has the same limit and it converges to 0. So this one would be the same thing. So I'm going to skip that one. So now this is a specific case when I have an alternating sequence. So the deal is you take the limit of just the positive part. If the limit of the positive part goes to 0, as it does in this case, the whole thing converges to 0. If the limit of the positive part does not go to 0, it can go to a nice number like 1, but as long as it is not 0, we say that the whole thing diverges.